Yeah, well, let's wait for Salim. I don't know.
By Salim, Salim, I don't know if he knows it, Mr. Chair. Could be he don't know.
Oh, no.
Otherwise, I'm just going to,
He should know.
to give you, the top down.
Sure, whenever.
And also we need to be sure that Nicolas is recording.
I'll comply.
Nicolas, are you okay?
Ah, here he is. I told you he's coming. I forgot. No, I want Salim to chair. He has to do his job. Salim.
I'm the chair?
I didn't know. Sorry, Salim.
That's fine. Sorry. Yes, that's fine. Okay. So next talk is Andrea. He's giving two talks about cosmic reionization, and the first one is entitled "The Physics of Cosmic Reionization."
Okay, let me thank you, Salim. But let me explain a little bit the rationale about the change. So first of all, my name is Andrea Ferrara. For those of you who don't know me, and I'm glad to meet you all today or in the next days. So the reason for the program is not because we are crazy, but simply because we thought after some, we could have realized before, but that it's important to have some historical or cosmic order in the presentation, in the sense that Pratica will, and other speakers, we will talk about the cosmic reionization. And so, because there are a number of speakers that are touching upon on that, I decided to shift a bit my lectures on the specific topic of first stars. And of course, first stars come before cosmic reionization, as we will learn today. And therefore, we thought it was more natural to go first stars today and tomorrow start reionization with Pratica and the other speakers. So, sorry, you were expecting Pratica, it's me, and you had to cope with me for at least 3.5 hours, including the breakfast, including the coffee break. And so, let's see, we will be concentrating on first stars. I will give you now the outline of the lectures. But first, let me go through a very, very broad overview of the timeline of cosmic events, just to put what you're going to say in a specific framework that will be more clear. So the sequence of events in the cosmos is basically as follows. So first of all, we know that at rescue 1000, it became energetically favorable for electrons and protons in the plasma, in the cosmic plasma, in matter bath, to recombine. And so that happened when the temperature was around 3000 K. First of all, this is a temperature that is much lower than what you would have expected. Have you ever thought about that? If you were to guess, or based on physical grounds, what is the temperature at which the recombination between protons and electrons would have occurred, would have you guessed that it's about 3000 K? If yes, so let's see. Who said yes? Please raise your hands. No, then raise your hand. So yes. Yes. No. 3, 4, 5. Okay. Answer no. Most of you. Okay, you know. So please, can you explain it to me? So why is it 3000, the temperature that you would have expected? First of all, what would you have expected? Because for me, I mean, naively, I know that the binding energy between electrons and protons in a hydrogen atom is 13.6 eV. So 13.6 eV, it's much larger than this. This could correspond to 0.3 eV. So why is 0.3 rather than 10.6? Here is the answer. Listen.
It's when you do the Saha equation out, it's like roughly where the like halfway point of.
That's technical. Suppose I don't know what the Saha equation is.
Oh, well, it describes the like the I guess, detailed balance of ionization states of hydrogen.
Still technical.
I guess. But yeah, like half of all hydrogens recombined.
No. No, there is a physical reason for that. And the reason is in the fact that the ratio of photons to baryons is very high. So that means that the entropy of the gas delays recombination, okay? And that, of course, you can see it quantitatively precisely with the Saha equation or in other ways. But the physical reason is that the entropy of the photon matter fluid is very high, and therefore that's delay recombination. Okay? So recombination happened. So after that, Redshift 1000, the universe remained neutral, and nothing happens until much later. So you have to wait for, say, maybe 100 or of the order of so million years after the Big Bang in order to witness the formation of first stars. And these first stars, for some reason, are usually called in the jargon population tree stars, where the tree is essentially a measure of the age, thinking like an age. Okay? So population 1, young, population 2, intermediate, population 3, very old. So these are the first stars that form in the universe. And as we will see, we will try to figure out what and how, what are the properties of the stars and how they form and when they form, and try to put everything in a cosmological context. So after pop-3 stars, which are the center of this lecture, these stars had very important feedback effects on the rest of the universe that will be discussed later on during the school. And in particular, here we are interested in the way in which the first stars contributed to the reionization of the hydrogen in the intergalactic medium. That is the inverse process of this one. Okay, so recombination, you go from ionized, neutral, and ionized again. So this is these are phase transitions that have been they are particularly important. And so why should you care about reionization? Some of the colleagues say, we know it happened, so that's it. But no, but there's more to that, because reionization, as we will see, has important effects on governing the way in which subsequent galaxies form. Okay, because it changes the essentially the boundary condition of the formation of galaxies, and that is particularly important and has dramatic effects on the evolution of galaxies and on their formation. And after that, by redshift 6, 1 billion years after the Big Bang, then this is over, and after that we witness the evolution of gravitational instabilities. They become nonlinear. They form massive galaxies, big clusters, and all the story that you will probably learn towards the end of this conference. Now, this is the sequence of the event, and so as I said, we are concentrating on this epoch. Now, these days, the fact that we are here talking about the possibility to detect these super early stars has become at least something that we can think of, because 20 or 30 years ago it was absolutely in the, in our dreams. But now, with instruments like James Webb Space Telescope and also ALMA and others to come like ELT, we truly hope that we can spot the formation of the first stars. Now, something that I will not touch upon, but it would be important, for example, with other people like Pratica or Marta, I don't know, will touch upon the formation of the black holes. Now, there is a difference between forming the first stars and forming the first light, because it's not clear whether the first light came, the first photon not produced by the Big Bang, came from stars or from other sources like accreting black holes. This is one of the open questions that clearly we need to clarify in the next years, and we hope to be able to do so. So first light and first stars are not necessarily equivalent, even though in this lecture I use them as synonyms. Okay, so before I start, let me tell you what is the lecture plan. The plan is divided in 3 chapters. So the 2 hours, the 2 lectures will be divided in 3 chapters. So there will be a break here and there, depending how we do with time. But so I'll start with the describing star formation in primordial environments. And you will realize that this is quite different from what we see today. Then something that we want to understand, which is crucial in many galaxy evolution models, also the simulations that Katarina was discussing today, are based on the fact that we assume an initial mass function not only for the population tree stars, but also for all stars. And finally, I will discuss, based on these findings, what are the properties that we speculate. Unfortunately, we still speculate on that, of the first stars, and we are trying to use them to infer a number of possible observables or effects through which we hope to identify and characterize the first stars. Now, just to be clear from the beginning, no truly genuine first star population tree star has been found yet. Okay? So this is a matter of, but my personal feeling is that we have made very, very good steps towards that goal, and I hope that in the next decade we will finally have a clear proof of their existence, even though we know that even from basic principle that there must have been the first star somewhere in the universe, and that stars had to form from an environment which is of primordial composition, like the one left over by the Big Bang. But I'll come back to that in a second. Also, before I start, I give you a list of reviews. Some are classical, some are newer. On first stars, there's a huge literature there. Actually, there is even a series of conferences that are dedicated to first stars. This is the number 4, but now we are at probably number 6. They are every 4 years. So if you're interested in this, just have a look at one of these proceedings, and maybe you can get into the next one, and so present your results there. So I'll leave you the slides so you don't need to copy all these references here. So let's start with the first chapter. So star formation in primordial galaxies or in primordial environments. So let me be very clear right away and try to identify what are the main differences between the present-day star formation and the star formation that must have occurred at the very beginning of the universe. So there are fundamental differences that will percolate to the rest of my lecture. You will see how these things are important and what is their role. So in present-day gas, so if you take a molecular cloud where stars form today in the Milky Way or in any nearby galaxy, you will see that typically the mass fraction in heavy elements, that is elements heavier than lithium, is of the order of 2% or smaller. Okay? So there's a tiny amount of heavy elements. Most of it is hydrogen and helium, of course. However, this tiny amount of heavy elements is very important because there are species that you can build up by combining the elements, or also to putting these elements into solid phase, which is we call usually grains or dust. Then it turns out that some of these molecules or species that you can produce from these heavy elements are excellent radiators. That means that they are very good at taking the kinetic energy or the thermal energy of the gas and transform it into radiation that is escaping from the cloud itself. So this is the important point. Okay? So there are radiators, efficient radiators of the thermal energy of the cloud. And so you can, based on that, you can define a thermal time scale that is a typical scale. We'll define it better later, but you can have an idea of what is the time that it takes for this cloud to dissipate all the thermal energy that it possesses, compared to the dynamical time scale, which you can take, for example, as equal to the size of the cloud divided some characteristic velocity, which is the sound speed. I also come back to that. Or the free fall time, some dynamical time scale, something that describes the dynamical behavior of the system. So in this case, because the species are excellent radiators, the thermal time scale becomes very short, and certainly much shorter than the dynamical time scale. And so that also favors the formation of stars for a reason that will become clear later. Don't worry. So, and that means that the cloud loses its thermal energy quite efficiently and goes down to temperatures that are very low. This is a temperature of 10 K. Can we make it even colder? Can I make it to 2 K? Exactly. So there is a floor below that I can't, with thermal processes, I cannot cool the cloud to lower temperature than the temperature of the CMB, which is 2.73 K RHU0. Is it true? Can I make it? Can you find any way to make it at 1 K? Is it possible? How?
There's denser of gas that blocks the photons.
No, it's a thermal bath. So you can't thermodynamically you can't go with thermal processes below the CMB temperature, but you can if you have adiabatic cooling. Okay, so you put everything in adiabatic expansion, then you can cool. And in fact, suppose there were no stars ever in the universe, and so we have the galaxies and we have the intergalactic medium. What do you think would be the temperature of the intergalactic medium today? Super hot? Super cold? Warm? Lukewarm? Cold. How cold? Who said cold? Yeah. How cold is cold? Okay, the temperature of the CMB would be a fraction of a Kelvin. Actually, it would be very much colder than the CMB today, because the intergalactic medium is expanding with the Hubble flow, and just because of this, you can get down to very low temperatures. But in the galaxy, this does not happen, because the galaxy is bound, and the molecular clouds are also bound in the galaxy, so you can't get down 10 K. Now, in primordial gas, instead, this is the combination left over by the Big Bang. Okay, so 76% hydrogen, 24% helium in mass, and the rest of tiny bits of lithium, beryllium, and boron. So no heavy elements, and so the situation is totally different. So the point is that hydrogen and helium are very poor radiators below 10 to the 4 K. So if you want to cool, if you have the same gas, but now with no heavy elements, you would never go below 10 to the 4 K. So you will never reach not even 10 or not even 100, okay? Simply because, as you will see in a second, hydrogen and helium are very poor radiators. So, and so the clouds are sitting there. They are not dissipating. Well, there is a tiny bit of dissipation, but essentially it's there sitting, maybe very slowly contracting. But the question is that you can go below this. So under this condition, it's very hard, as we will see, to form stars. And so the first thing that you have to realize is that if we are here today, you have to thank these molecules, so molecular hydrogens. The molecular hydrogen molecules, as we will see, are the reason for which the first stars could form. Without molecular hydrogen, nothing would have happened. So clearly, molecular hydrogen is an important ingredient, and we all understand why. So now, how do I form molecular hydrogen is one thing, and the other thing is what happens without molecular hydrogen. We'll come back to that later, but for now, let's concentrate. Let's suppose you have a gas of primordial composition, like the one that we had at the very beginning, and therefore we ask ourselves, what are the main cooling processes in this primordial gas? We have essentially 4 different channels, which are very important, and I'll show you the summary and the combined picture. But so just go back to physics that you should know, but it's good to refresh. So the first process is a radiative recombination, the one we have already discussed. So basically, you have the thermal energy lost in the particles that are recombining, a proton and electron in the case of hydrogen, and goes to a photon that is emitted in the process. So now there is an issue that you have to be careful here, because if you take an electron and a proton and you recombine it to form an hydrogen atom, okay, then if recombination occurs at the ground state of the hydrogen atom, then the photon that is emitted has an energy which is larger than the binding energy, equal or larger than the binding energy of another hydrogen atom. So that would cause ionization. So the net balance would be 0. So because you're exchanging that energy from one atom to the other. And so when we compute on the cooling process due to radiative recombination, we only need to we have to consider only recombination that occur at levels that are excited, so with a quantum number n larger than 1, so 2 and above. And so usually this is called, I'm sure you've heard about that, this is called case B recombination, okay? So where you cut off the recombination that occur at level 1. The second process is collision ionization, and so this is due to the fact that you're burning thermal energy of electrons into ionization energy that essentially breaks the hydrogen atom again. And so you have a cross-section for the process that depends on the energy of the particle and the binding energy, where of course the binding energy is 13.6 eV or 1 Rydberg. And so then you take this cross-section, you average over the distribution of the electrons, which is typically Maxwellian, and then you get your rate of energy loss. The third is the most important one, as we will see. It's a bound-bound transition of hydrogen atom, and this is the most important cooling process, around 10,000 K. So it's the collision excitation of an hydrogen atom by an electron. So the internal electron goes to the higher level, it decays, and it's emits a photon, which typically it's a Lyman alpha photon if you are there, or any other photon that you have been able to excite. And so this, again, carries away the thermal energy of the gas into radiation. And the fourth one is the thermal Bremsstrahlung, or sometimes also called free-free. And so this is the radiation emitted by an accelerated charge that is in the Coulomb field of another charge. And again, here we have a cross-section that is known from atomic physics that depends on quantities like the number density of electrons and protons, the Gauss factor, frequency. This is a well-known formula. And again, you have the cross-section, you integrate over the velocity distribution, and you get the rate of energy loss. So these are the only 4 processes that you have available in a primordial gas. There's nothing else. So very simple physics. So if you put everything together, you build something that it's called the cooling function. Okay? So the cooling function, first of all, has units of erg per second, so it's a rate of energy loss, also multiplied by a centimeter cube. So when you take this and you multiply by a density squared, because all these processes are two-body processes, so they depend on n squared, then you get the rate at which this gas, sitting at the initial temperature T, loses energy to radiation. Okay, so that tells you, basically, if I put a gas at any given temperature, say 10 to the 7, I know from here that it will lose energy at a rate of about 10 to the minus 22 in those units. And so I know, essentially, how efficient is the energy loss due to the presence of this species due to the presence of this species with respect to the initial temperature. Now, the four processes that I mentioned here are shown by the different lines. And you see that there is a clear shape. This is the total. The solid line is the total. And here, the peak is dominated by the bound-bound transition. And you have the same bound-bound transition also for helium. Okay? This is for hydrogen. This is for helium. And as you go to larger temperature, you approach the free-free regime, where the only process that matters is the free-free. So you have a very hot gas. Free-free will be enough. Now, if you look at this figure, you immediately realize the problem of first star formation. First star formation, you have primordial gas. And the primordial gas cannot cool below 10 to the 4 K, okay? Maybe 8,000 or 9,000. So if I have a gas which is initially sitting here at temperature, say, 5,000, 4,000 K, it will do nothing. So it will just sit there because the temperature will not change, because there is no process that is able to produce this energy loss. But if you don't lose energy, basically what happens is that that cloud cannot contract because it's supported by its own thermal pressure. And so this will never form stars. It will be a cloud sitting there for an Hubble time with nothing happening. And so that could have been the fate of the universe, right? So without anything else, if we only knew this physics, we should consistently conclude that stars never form. Clearly, there is something wrong here, and I'll come back to this point. So this is the problem. Okay, now we will deal with that. Before I do that, so let me introduce some key timescales that will be important through this lecture and in general for understanding this type of problems. So having defined the cooling function that I showed in the previous slide, what we can do is to define a cooling time. So the cooling time is the time that it takes for the gas to decrease its temperature by 1 over E, an E-folding time. Okay? And so using the energy equation, or the first principle of thermodynamics, if you prefer, you can find that dimensionally, the cooling time is proportional to, is linearly proportional to the temperature in the denominator. But then you have also this term that depends on temperature, which is the cooling function. And then you have the density. So the highest is the density, the shorter is the cooling time. There's no question about that. But with the temperature, it depends on what you're prescribing for lambda. Okay? So that cooling time gives you an idea of how long will it take to the cloud to cool down from the initial temperature T. Now, the freefall time is the second time scale, and this is very simple Newtonian dynamics. You can show that basically the time that it takes for the cloud to collapse ideally to a central point is called the freefall time. You can also derive it from linear instability analysis of the fluid equations, but the answer is the same apart from some factor here. But the key thing is that this is very simple. So free fall time, it's purely dependent on density. Okay, I will indicate rho is the mass density, n is the number density of particles. So there is a mean molecular weight in between the two. But basically the same. So T is proportional to 1 over rho to the 1/2, 1 over square root of density. Again, the higher is the density, the shorter is the free fall time. So same behavior as here. So whenever you have something which has larger density, not only will tend to cool faster, but also to collapse faster. So having high density is a good starting point if you want to get going so that the cloud does something rather than staying still there forever. And because we are dealing with cosmology here, there is a third time, which is the Hubble time. And the Hubble time, of course, is the inverse of the Hubble parameter, which is itself a function of redshift, and itself function also the cosmological parameters depends on omega matter, omega lambda, and omega radiation. So now, usually, so that something happened, these two times must be shorter than the Hubble time, because something must happen during the lifetime of the universe. Okay, you can think of the Hubble time as closely related with a factor here to the age of the universe. Okay, so we have these 3 times, and then already in the 80s, people like Martin Rees, Jerry Oestreicher, and others, Joe Silk, were starting to think, okay, that these time scales must be relating among them, and it must, to the 0 order, being able to define what's happening to our system, to our cloud or galaxy. As we will see when we go to very high redshift, the difference in between clouds and galaxies becomes rather fuzzy, but that's for later. So we have 3 times, we have 3 regions. The first region is the region in which essentially the free fall time and the Hubble time are much shorter than the cooling time. So that means that it takes forever for the cloud to cool, and therefore it will essentially remain there. This is the nothing happens case that I described before. Then we can be, so this is not interesting for us. Then there is an intermediate region where the cooling time and the free fall time are just shorter than the Hubble time, but still the cooling time is long enough that it's much longer than free fall time. So again, maybe the cloud starts to slowly contract in hydrostatic collapse, but this is not the type of dynamical violent collapse that leads to fragmentation and increase of the density that we are looking for. These conditions are only found here in a region where the cooling time is much shorter than the Hubble time. And so these are the conditions that lead to the dynamical collapse. And if you rotate this figure like this, you see that this curve here is nothing else than the cooling function that we defined before, right? So if you look at, if you rotate the figure 90 degrees, then you see that these regions are very dependent on, as it should be, on the shape of the cooling function. And so again, we can see the same problem that I mentioned before in a different way. So if you are down here, so if you have temperatures of 5,000 K, and there's not by chance that I mentioned this 5,000 K, because this is the temperature of nonlinear structure that we have available. We'll come to that later. But so if you're here, then you're still in the cannot cool avoidance region. And so this is the problem. So it was realized early on that already in the 80s that we have a problem, because how could the stars possibly form in these conditions? And so, surprisingly enough, it was not before the end of the 90s that people start to realize that the solution was to have another species. And the other species that you can form, starting from these initial building blocks, hydrogen and helium, is molecular hydrogen. So we need to introduce molecular hydrogen in the scenario. And that, for even if molecular hydrogen is the most simple molecule that you can build in nature, basically. In fact, when I talk to my friend chemists, they say, what, H2? I mean, do you consider a molecule? They don't even consider it a molecule, basically, because it's so simple that they don't care. But fortunately for us, it has all the qualities that we need in order to solve the problem. So why is that? First of all, the key fundamental physical reason is that molecular hydrogen has transitions or energy levels that corresponds to both vibrational and rotational transition, because it's a molecule. It can rotate like this, or it can also vibrate. So these two modes are sensitive or can respond better to collisions with particles that are embedded in a gas of 10 to the 3 to 10 to the 4 K for the vibrational transition, or even below 10 to the K in case of the rotational transition. So this is good. Okay, we have a new way, we have a molecule that can respond to collisions with this type of particle, low energy particles, but we have a price that we have to pay, is that molecular hydrogen is made of two atoms that are the same, two hydrogen atoms. And so that means that there is no dipole moment. And if you have no dipole moment, the absorption coefficients are very small. All the Einstein coefficients are very small. But nevertheless, we will see they are enough. So the thing is that we need to add a new piece to our cooling function that before was only taking care of hydrogen and helium. But now we can add the cooling function that is contributed by molecular hydrogen. And these transitions are mostly excited, can be excited by collision with hydrogen atoms. So an hydrogen atom that hits a molecular hydrogen, or collision between hydrogen molecules themselves. Okay? So there are two ways. This, as we will see later, these are very not super well-known coefficients, I have to say, but fortunately there's a way out. And so molecular hydrogen is there. Now, one thing that I need to explain at this point before we go on, because it will become important later. So then whenever you do this calculation to compute the cooling function, you need to study or determine the population of levels in the various transitions, because those are needed in order to compute the emission from these molecules. And so this level population entails something which is very fundamental. It's not relative to molecular hydrogen or any other species, but it's a general physical process that is called the critical density. Okay? So the critical density is a very important density. Can I use the blackboard? Yeah, but can you see if can you see if there are lights? Yeah. So what I'm going to do is just assume that you're taking this very simple case. I just want to explain the concept. Okay. So we have an atom. Yeah. Yes, I think so. I tried to write big characters, so you have an atom. So suppose just a simple two-level atoms in which we have population of electrons n1 and n2 in the two different levels. And so electrons can go up and down, okay, depending on what. First of all, they could be excited by collisions. And so we have a coefficient that is C12, that is the coefficient that drives electrons from the ground state to the excited state. And then we have the analog process that is called collisional de-excitation, that I call C21, that brings electrons down to level 1. And there is also another process, which is the spontaneous emission of a photon. Okay? So there are two processes that bring in things down, and one process that brings electrons up. So the level population is nothing else than being able to write what is the ratio between the electrons, atoms that have electrons in the ionized state, and atoms that have electrons in the ground state. And so this is very simply will be equal to the rates of things of processes that are pushing electrons up or down. So up is, we have seen that is collisional excitations. So we have C12 times the electron density, because we are assuming that there are electrons that are doing the excitation. And then we have the rate of these other two processes. So it's A21 plus NE, or C21 times NE, as simple as it is. So this is the level population for this simple atom. Of course, molecular hydrogen, many transitions, so it's much more complicated. But this is trying to give you the concept. Now, if you look at the denominator, you can ask yourself when these two terms are equal. So I'm imposing that A21 is equal to C21 NE. And so from this, I can define a density which I call the critical density, and crit, where these two are equal. And therefore, by solving this very difficult equation, I can find that N critical is equal to A21 over C21. Okay? This is the critical density. Now, let's see what happens when you are above or below this critical density of electrons. So suppose first that we are in a regime where N is much less than the critical density. Regime number 1. Okay? Low density. So NE is much less than the critical density. So the first thing that I could do is just neglect this term compared to the other. So I get that N2 over N1 is approximately equal to C12 NE over A21. Good. Now, the emission that I get from this gas, so the intensity of the light or the photons intensity emitted, is simply equal to the number of atoms that are in the level N2 times A21, which is the rate at which they decay. So they emit a photon. This is the only process that produces a photon. Okay? The other two are just collision with particles. Okay, so then I can use this relation. I can substitute this. So I get an N2 is equal to C12 NE over A21 times N1. And then I have this A21, which goes away. And so we find that this is equal to C12 NE N1, which is proportional to N squared. Okay? So the emissivity of a gas which has a low density, below the critical density, goes like N squared. So there's a strong dependence on the density. Let's see the other case. Case number 2 is the one in which NE is much larger than the critical density. Then I follow the same path, and I have N2 over N1. In this case, I'm neglecting A21. NE and NE go away. And so I have that this is simply equal C12 over C21. These coefficients are function of temperature only, so they're not depending on density. And again, I can compute I in this case. That remains the same, so N2 times A21. I substitute now for this, and so N2 is equal to C12 over C21 times N1 times A21. And so this is proportional to N. So what's happening is that the gas emits, if it is at low density, it emits like N squared. But when you get above the critical density, then it starts to emit N. Now, based on this, can somebody explain me the physics of this? Why do you think it's like the physical? Well, sure, we see it from there, but why do you think, can you explain it to me physically? Think for a second while I'm drinking because I'm thirsty. Please.
I mean, if you have a high enough density, then it's more likely to cool by like the two volume interactions, which are like dependent on N squared, right? And then in the lower density regime, then you transfer into this relation where it's like proportional to N because it's cooling radiatively.
I was happy with the first part. I'm not sure I got the second part, so it might be right, but the first part was basically okay. So essentially what's happened is that if you have, think of an atom, you're sitting in the excited level. And so at some point, if nothing happens, at some point it will spontaneously decay. But before that, an electron comes and brings the electron down. So you're de-exciting without emitting a photon. And so that photon does not happen. So if the density is very high, the collisions with the electron become more frequent than the rate at which the spontaneous emission would occur. And so that is the point. So when the density is high, which is strange, right? Because you would think that the more I increase the density, the more bright the thing will become. But that's not true. Because then beyond a certain critical value, then this is not happening, and actually the emission will decrease. This will be very important later in the second, maybe in the second lecture, but keep it in mind. This is a general concept that is very important in astrophysics. Of course, each line has its own own value of the critical density because it depends on the Einstein coefficients. Okay, so keep that in mind. So this is the summarized here, N squared versus N. Now, we have learned about this. So what's happening? Now, if you include now the cooling function due, or the cooling terms due to molecular hydrogen into the cooling function, you get something like this. This is still our lambda. So the cooling function versus temperature as before. But all I showed you before was somewhere here, okay? So you look at the temperature here. I'm showing just the graph between 10 to the 4 and 10 to the 2 Kelvin, okay? So now all this part were 0 before. Remember the previous slide here? Yeah, so we are just looking now at this region here where we had the problem. And the inclusion of molecular hydrogen does this. So it populates all this region of low temperature with a non-zero cooling function. Now, there are several lines, so let me explain you. And the several lines are there, but should not be there. But they are there because there is still a disagreement among various groups on the actual value of the cooling function of molecular hydrogen, believe it or not. So people disagree by even orders of magnitude. For example, we have here, I'm showing two different cases. A low density case, which is these three curves here, and the high density case, which is these curves here that collapse essentially into the same one. So let's start from the low density case. So these are three different groups that I marked with initials. But you see that the discrepancy is pretty large. If you go here, these are almost 2 orders of magnitude, right, in the cooling of molecular hydrogen, which is quite surprising. Always surprised by this thing. Because we don't know exactly all the coefficients for all the various transitions. This is very hard experimental work. And not many people are happy to spend the entire life in computing to the third figure what is the value of that coefficient. So there are discrepancies. But these are the bad news. The good news are that when you go to high densities, 10 to the 6 or so, all these 3 groups are happy. They go to dinner together and they agree. And so they have a nice agreement that you see here. And this is good news because the gas in which we want to form stars typically are high density environments, right? So we don't form stars anywhere with 0.1 particle per cc. So when we get to 10 to the 6, they all agree and we are happy. So let's assume that they are right. And this is the curve that you get. So clearly, you are creating a region here where the cooling is not negligible, and that means that molecular hydrogen has opened up a new channel for the cooling of structures that are relatively cold, 1,000, 2,000, 5,000 K. And that was impossible before. Without molecular hydrogen, that was impossible. And now your legitimate question to me would be, okay, but this if molecular hydrogen was there. And we are talking here about redshift 30, 40, 50, 100. Okay? So was molecular hydrogen there? Could it form? That is probably that was the bottleneck of many of the researchers before, because there was an intrinsic bias or preconception. It was too hard to form molecular hydrogen at this high redshift, so people never really considered this issue until, as I said, a little bit more than 20 years ago, so pretty short time ago. Okay, so now, what do we know of molecular hydrogen? The first thing, do you have an idea how molecular hydrogen forms? What is the best way to form molecular hydrogen? I mean, yeah.
I only know in the local universe that it can be easily formed on dust grains.
That's perfectly correct. That's what I wanted to hear. And in fact, this is exactly where, by far, the most important mechanism that we have today in order to form molecular hydrogen. So you stick two hydrogen atoms on the surface of a dust grain. Why do you need a surface? Because you keep them there, keep them close. And then, because the surface of the dust grain has some thermal agitation, because it's a solid, so it vibrates, so these hydrogen atoms that are on the surface are bouncing a little bit. They're kept together by van der Waals forces. And so they bounce until magically they meet and they combine in order to form molecular hydrogen. The problem we have is that we need dust. Right, but how do you make dust? From stars. But what if you don't have stars? So we are in a loop, right? It's a conundrum. So we can't use this thing. You can't use this idea that we see today that molecular hydrogen is formed on dust surfaces. So what else? There is another tiny, what would you suggest? Collisions between what and what? Tough. It's very tough because it's very tough to convince two hydrogen atoms to combine to form molecular hydrogen. For the same reason that I told you before, that there are two equal molecules. So quantum rules do not allow that because you don't have dipole transitions. So It's still possible, but you have to have a trick. And the trick that sorry? Helium. Yeah. Sorry?
With electrons?
Yes, in some sense it's with electrons, but more than electrons is through a catalyst, which is you have to create a third particle that introduces the two atoms together and then goes away. And that is called the catalyst. And there are several catalysts. It's not only electrons is one possibility, but there are other possibilities. So you need to create a catalyst which is usually H minus. So the most important catalyst is H minus. So, and this is the first channel that we see here. So this is called the H minus channel, and then consists in the following. So you take an hydrogen atom, you stick an electron to it, and then you produce an H minus atom, a negative ion, and you emit a photon. Now, this H minus can collide with another H, and this time you have electric dipole, you can form an H2 molecule and then release the electron again. So you see that H minus is purely passive there, so it's a catalyst. So it helps the reaction, just providing that amount of asymmetry that, that is needed to form the molecular hydrogen. Now, you can do the same with a proton. So your answer was correct, but you can also do it with protons. And in fact, as we will see, there are cases in which this is important. So you do the same. H plus a proton, you get an H2 plus, and then the H plus H2 plus, you get into H2 again. So these are important, the most important reactions that you can use in the early universe where you don't have dust to rely on. Okay. Now, however, nothing comes for free. So we are pushing the problem to having enough electrons and protons that are free electrons, free protons. And so, of course, these conditions require then you have an ionization degree in the gas, and I'll come back to the. For now, you have these electrons. So we are talking here very high redshift. There are also other reactions, but as we will see, they are not particularly useful for our problem, at least. So we have three-body reactions in which, again, you create an asymmetry because now you have three particles, and then you go through this chain. And at the end of the day, you form molecular hydrogen. But this is only possible with very high densities of the order of 10 to the 8 particle per cc. But for us, it's already too late, right? Because we want to go from, say, densities of 10, 100 particle per cc to 10 to the 8. So if this becomes important at 10 to the 8, it's not very useful for us. And finally, you can also have another condition in which you have the two hydrogen atoms, but one is in an excited state. So again, you have an electric dipole, and then you can form H2 directly. So this is important at redshift larger than 1,000, where the CMB photons destroy the other species, because this is the other danger. So even if you have H minus or H2 plus, if the CMB is energetic enough that it can ionize or break the bonds for those molecules, these molecules are destroyed. And therefore, it's even those two channels are not working if you are at too high redshift. So these are the formation channels. However, so should we be satisfied with this now? Now we know how to. Yes, please.
Sorry if you already said this, but why does it matter that one of the hydrogens has to be in the n equals 2 versus the n equals 1 state? Like, why is it?
Because you have an electric dipole, because the distribution of electrons in the n equal 1 is different from the n equal 2. Okay, so that creates a dipole. Now, are we happy? We have seen there are 4 ways to form molecular hydrogen. Are we happy or not? Should we consider the problem as solved or not? Yes.
should know which formation channel, if there is one, is efficient at the scale of a quantum?
Yes, but I'm still worried that we have to solve another problem before that, more fundamental. Think for a second. Yes.
I mean, we still have to get like a certain ionization degree, right?
Yes, that's also true. So, so we need ionization. We need this to understand which one of these channels is more efficient. And
I would think that the free body reactions are way more unlikely because you need free.
I agree. So we can concentrate mostly on this. I'll tell you why, but yeah, yes. So we can concentrate on this too, and we have to make sure that we have enough ionization. Something more, guys, more obvious.
So we need electrons.
Well, yes, ionization degree is important, so that's what we are saying. But there's something more. Yeah, two hands here. Go ahead.
How can we explain such degree of ionization after the recombination era and before the appearance of the first stars?
I totally agree. Let's say that this is all these things are all in this line here. Fine. But something more. There's a head.
Maybe the temperature so that it doesn't again dissipate and fall.
Bit more.
Hydrogen, like the molecular hydrogen doesn't stay as molecular hydrogen. So
Yeah, this is formation. There you go. But there's also distraction, guys. So it's not enough to form it, but if you form it, then it goes away immediately. So what are the ways in which you can destroy molecular hydrogen? Unfortunately, there are many. So there are at least other 4. And one is very dangerous in particular. So there are 2 obvious dissociation channels that have to do with the fact that you have impacts with other particles. And in particular, you can have impacts with neutral hydrogen, or impact with protons, or impact with electrons, whatever you have, essentially. So they are important in different regimes. So first of all, for the hydrogen atom, the temperature had to be at least 2000 K, because lower temperature collisions are not sufficiently energetic to break the bonds of the molecular hydrogen. This one with the protons and electrons, I have to say, are important whenever the gas is highly ionized, because you need to have a lot of either protons or electrons. Electrons are always subdominant in this sense because obviously the kinetic energy of the electrons is lower than the protons. So in general, the destruction occurs through this channel. But the most important one is not even this. The most important one is the photodissociation. So this is a very important process that is called the 2-step Solomon process. It's very important, not only for first stars, but in general in the universe, where you can destroy molecular hydrogen via using UV photons in a specific energy band that is called the Lyman-Werner band, that is between 11.5 and 13.6 eV, so just below the ionization. So these are non-ionizing photons, okay, just to be clear. So these are 11.2 to 13.6 eV. And so what happens is that a photon can be absorbed by a hydrogen molecule, goes into excited state, but some excited states have a non-negligible probability that whenever you return to the ground state, the molecule breaks. Okay? It's a quantum mechanical effect. And so if you have a lot of UV radiation in that band, in the Lyman-Werner band, then your molecular hydrogen is destroyed. So you see that the answer to the question is not obvious, because you have to not only to compute what is the formation rate of the molecular hydrogen, you have to compute what is the destruction or dissociation of the molecule, and you have also to prescribe what is the environment in which all these processes are going on. And so this is a non-trivial calculation that fortunately some people have done very carefully for us, and the results are in the next slide.
Photodissociation is a big process.
The photon is, that's correct. So the mean free path, so if you have a cloud that is irradiated, for example, by external UV luminosity, so you have these UV photons that are trying to penetrate the cloud, and if the cloud is a column density that is sufficiently large, it can self-shield to these photons. And so the typical column density to do this is relatively small, 10 to the 14 inverse square centimeter. And so there's self-shielding as well. But it requires that you have already something that is dense enough and compact enough to self-shield. So if you are still in the diffuse, you want to go from the diffuse phase and build the clump, then on the way you are exposed to this radiation. And so it's very hard to start the process, right? Now, this is a graph that shows a resume of essentially all the things we have put together now that describes the evolution of different species as a function of redshift. And note that here, this is in log, okay? So this is in log, so this is today, redshift 10, 100, 1000. So the CMB is somewhere here. And so what do we see? First of all, let's start to look at the top two curves. The first curve is the abundance of neutral hydrogen. And you clearly see that here, this knee here in the purple curve is what? Is recombination, okay? So this is where recombination, which is precisely increases the amount of neutral hydrogen from 0 to 1, okay? Not to 1, a little bit less. And in fact, if you look at the electrons, the electron fraction goes down. Initially was 1 because the gas was fully ionized. At recombination, it recombines, and then it goes down to some level, which is of the order of 10 to the minus 4. Okay? So this is called the relic fraction of free electrons, and it has to do with a very general phenomenon, again, in cosmology, that is called the freeze-out. So what is the freeze-out? Well, the freeze-out is a process that occurs almost by definition whenever you have to do with interactions that are two-body interactions, okay? And this is why. So the physical hint, then you can work out the details if you're interested, or we can talk about that. So the physical hint is the following, that the time scale for two-body interaction depends on 1 over density, okay? And this is simply because you can think that if you have, well, I can write it here. So if you want to write the abundance, the change in the abundance of a given species as a function of time, it will be dN by dt equal to the interaction rate times some coefficient A that describes the interaction. So basically, dimensionally, you have that T is essentially proportional to 1 over N. Okay? So the time scale for the reaction is 1 over the density. But in cosmology, we know that the density as a function of redshift increases like 1 plus z to the cube, okay? At least for normal matter. And so that means that the interaction time decreases like 1 plus z to the minus 3. Good. Now let's look at the Hubble time now. The Hubble time, we know that the Hubble time is in the matter-dominated era is proportional to 1 plus z to the minus 3 halves. So that means that there will be always a time at which the reaction time goes below the Hubble time. So it becomes, goes above the Hubble time. So the reaction time scale becomes longer than the Hubble time. So that means that that reaction would take forever to complete. And this is exactly what happens to electrons. So what is the reaction that we need to consider here? The time scale of what reaction? It's very simple. What is the reaction that we are writing here? What recombination, okay? So the recombination time scale becomes longer than the Hubble time. And so not all the electrons are able to find a partner, a proton partner, to recombine and form a neutral hydrogen atom in an Hubble time. And so that means that there are few electrons that are unlucky enough that remain single, and therefore you have this fraction of electrons that will not change anymore. They will are leftovers. So these are relic electrons, and this is why we call this the freeze out, because the density is frozen. It's frozen at this level, will not change anymore with redshift. Okay, so now remember that before you stated several times that the ionization degree is important, right, for all the reaction of formation of molecular hydrogen. And fortunately, here what we have. So fortunately, the universe was kind enough to leave some electrons and protons so that we can use them, or the gas can use it to form molecular hydrogen. And that's what's happened. So this relic fraction here allow the formation of molecular hydrogen. Now, molecular hydrogen evolution is the black curve here. So you see, initially there was no molecular hydrogen, and then we went through stages in which different processes that I mentioned before become dominant, okay? And then there is a switch from one process to the other. So initially, the number 4, the excited hydrogen channel was the dominant one. But then there were no more excited hydrogen atoms, so we turned to H2+, and finally to H-, which now this is in log, so keep in mind that this is the major jump, right? Because you go from 10 to the -8 to 10 to the -6. So the most important process is the H-. H- that is formed thanks to the presence of these electrons. And what these electrons remain in a fraction that is about 3 times 10 to the -4. And similarly to the electrons relic fraction, we also have an H2 relic fraction, the same way as the electrons. So this reaction also throws out. And so the value that we finally got at the end of the story, when everything stops, and that happens around redshift 100, it's of the order of 10 to the -6, okay? The value that you can read from here. So the rule of thumb is that together with the relic fraction of electrons, the universe was also left with a fraction of molecular hydrogen that was non-zero. There was molecular hydrogen in the universe. And that, for our goals of forming the first stars, has been fundamental, as we will see. Now, together with this relic molecular hydrogen, there are also other molecules. H2 is not the only molecule that you can form, but you can form HD. We will see that this is also add some twist to our scenario. We'll see it later. And also you can form molecules with ridiculous abundances, and like 10 to the -20 or so of the hydrogen lithium plus, lithium H, and so on, and helium H+. So these are essentially all the molecules that you can form out of a primordial gas made of hydrogen and helium. Okay, so now we have seen that without molecular hydrogen, there would be no way to cool gas below 10 to the 4 K. Fortunately, we said that if we have molecular hydrogen, then we can in fact cool these objects to lower temperatures. Then we found out that molecular hydrogen can be indeed present in the early universe. And so, is the problem solved? No. And the reason to convince about this is the following, that we can plot now a version of the cooling diagram of the 80s in a more modern form, in which we now have included in the calculation of the cooling time and in the cooling function also the effect of molecular hydrogen that we were saying it was necessary. But yet, as you will see, that does not solve the problem. And so this is, as I was saying before, this is a modern version of the cooling diagram, but let me explain you why it's different. First of all, we have the same three regions. Cooling time smaller than the freefall time, intermediate region, and the region where nothing happens, where the cooling time is longer than the Hubble time. Now, instead of plotting temperature and density, we plot different quantities here. And because now we are thinking about the dark matter halos. So we are connecting with galaxy formation. And as we have seen from the lecture this morning, these halos that are the nonlinear evolution, the nonlinear phases of the evolution of the gravitational instability. So these dark matter halos can have a given mass, and the mass can be also translated into a virial temperature. So we can talk about virial mass or virial temperature almost interchangeably, even though the relation is not linear, but higher virial temperature is higher mass. And the other quantity that identifies the halos is the redshift at which they virialize. Okay? So whenever their density in dark matter became equal to about 100 times the background mean. Okay? So this we set this time as the virialization redshift. So in this frame, we can plot, I don't know if you see the lines here, but there are lines that are perpendicular, and this is 1 sigma, 2 sigma, 3 sigma. So these are different peaks. Yeah, unfortunately, the projector is not doing very well here, but no problem, I can read it for you. So 1 sigma, 2 sigma, 3 sigma, and these are lines that are going almost perpendicularly here. So they are like this, okay? So 1 sigma are very small amplitude fluctuation of the field. 3 sigma are very large fluctuation of the field. And however, they are rarer. Okay, so that means that they are more difficult to find. In any case, if you look at these quantities, 1 or 2 or 3 sigma, in the redshift range in which we would like to form the first star, so 10 to 50, they are all essentially sitting in this region where nothing happens. So now we would like to find things that are actually in the upper regime where the cooling time is much shorter than the freefall time. But yet, it's very hard to find these objects. Okay, it's very hard to find these objects at the time where we want to form the first stars. So the point is that even including this molecular hydrogen is not the solution. Okay, so what would you think about that? So if not even, we're seeing that there is 10 to the minus 6 particle per cc of molecular hydrogen. They were there, but yet they are not helping us. So the objects the halos that are there are still in a regime where it is not possible to form stars. So what's the solution? Something else must have happened, obviously. Shocks, what do you mean by that? It's a word. I don't know what you mean. It's kind of. Kind of, yes, it's part of it, but it's not really. You don't need a shock for. You don't need a shock. Of course, if you have a shock, the idea is it goes in the right direction. So you want to increase the density, but why do you want to increase the density? Sorry? Yeah, so you want to increase the reaction rate and the formation rate, because that depends on the density of the gas, right? You are seeing that goes. Yes, in fact, I'm done. I want to leave this now for questions. 10 minutes for questions, and leave you with this unanswered question for the next lecture, so you can think during the coffee break. We'll stop here for now, and then we go to the next lecture, and I'll tell you what is the solution. Yes, let me see. Sure. Questions? Yes, please.
I have a very naive question.
Please.
I suppose that this scale, we can exclude the impact of dark matter. Consider region too small to be impacted by the dark matter itself, I suppose.
The effect.
The collapsing of the cloud. The first collapsing
Is exactly the point. So the thing, as we will see later, in order to, the abundance that we have computed before, that 10 to the minus 6 molecular hydrogen, is in the mean density, so at the mean intergalactic medium density, okay? But now we are so the baryons could not collapse, because we are saying that the collapse cannot occur because the gas cannot cool. But fortunately, there was that dark matter.
Because I'm not sure to understand what is the physical scale, we are speaking about here.
This is a general. So far, there were no scales because there was no structure formation notion in the problem that we are going to introduce now instead. And in fact, the answer. Yes, it's partly shocks, but it's compression. It's compression, but not by the barriers itself. Because if there were no dark matter, indeed, we will be in trouble. There will be no way to collapse. But because there was dark matter, and these baryons were not there in the middle of nowhere, but they were forced to collapse in the gravitational potential well of dark matter, which is not only the dark matter perturbation grow constantly with time, but they also, omega matter is 7 times larger than omega baryonic. And so that means that the gravitational field is dominated by the dark matter. So it was the dark matter that forced the baryons to get together, compress, and eventually increase the density so that more molecular hydrogen is formed. And therefore, at that point, the gas is able to cool, compress, collapse, and form stars. So this is the point that I told you the secret, but I'm glad that you found the correct solution directly, because this is the dark matter. That's what we'll see after the coffee break. Other questions? Yes. When we do the computation?
For the energy level here, we are at the minimum of the Kelvin, so how can we say that we are the same?
I'm not sure if I understand the question. So we have for example, if you take, I don't know, hydrogen, but you can talk about molecular hydrogen. So you have energy separation between levels which are independent of the temperature. So, the Lyman alpha is the Lyman alpha. It's not dependent. So it's 10.2 electron volts. So that jump is fixed. So it's nothing to do with the temperature. Maybe you're talking about the excitation. So it's not the difference in the gap in the energy that matters. That is fixed because it's set by the structure of the atom, how many the charges and whatever. While the rate at which this transition is occurring, that depends on the temperature. And why it depends on the temperature? Because the temperature determines what is the velocity, the sound speed, at which impactors hit the atom. Okay? So this is the rate of impacts that could increase the rate of transitions or excitations in that sense. But the energy gap is not dependent on the temperature. More questions? No? Then we break for coffee?
Half an hour?
Yes.